Today we'll be looking at Ramsey theory, what Ramsey problem is, how it started, and why it is difficult, and why people are bagging their head for such a long time. Yeah, so in the last session, we discussed pigeonhole principle and one very popular pigeonhole principle problem. Let me just go through that thing again. Yeah, here I have introduced what a Ramsey number is, but okay, maybe, yeah, I'll write here. Okay, so this actually started as a problem from social science. In 1995, 1915, a Hungarian sociologist, Sander, he was studying friendship relationships among children, and he made a following observation: that suppose you have a group of 20 children, then any four kids among them are either mutual friends, or there are four kids such that no two of them are friends. That is what he observed. Okay, so how do we deal with these kind of questions? He was not a mathematician, so yeah. What we can do? Okay, we'll start with small sample. That suppose we have six children. Then the claim is that we like draw the relations between them, and the claim is that either there are three kids who are mutually friends, or there are three kids such that no two of them are friends. Can you prove the following claim?
Can I say?
Yeah, go ahead.
We color any edge between two vertices red if they are mutual, if they are friends, and say black if they are not friends. So consider any vertex. It has five other edges. So by PHP, some three must be of the same color without loss of generality red. So if the three, yep. So now you consider the three vertices where this edges go. If any out of these, if any of the among them edges is red, we get a red triangle.
Yeah.
If it is not, then we get a blue triangle joining these three vertices.
Right. Otherwise, we got this triangle such that all of them are mutually strangers.
Yeah.
So yeah, this was good. This was a fairly easy problem. That when we have six things, what can we do? Like we label the points. Like the points are called vertices, and we suppose that they are the kids, and the edges are supposed to be what the human relation, either they're friends or unknown strangers. So can we what convert this thing into mathematical language? That here we had six children. We convert that to graph with six vertices. What else we can do? We have like either three of them are friends. We can, how do we replace this statement
three edges which has the same color.
Yeah, can you say that a monochromatic triangle?
Yes, monochromatic triangle.
Yeah, monochromatic polygon is a polygon such that all of its edges have the same.
Yes.
And like three enemies can be, or like three strangers can be defined in the similar way. So our claim is that if there is a graph with 6 vertices, so now we do the mathematical formulation of that. You have a graph, 6 vertices, colored with two colors. So edges are colored with two colors. And our claim is that there exists a monochromatic triangle. That is the thing. Okay, now suppose what? Consider the graph with 5 vertices. Does this thing necessarily have a monochromatic triangle?
No.
No.
Can you give a counter example?
Star in star and the pentagon, star of first color and pentagon of the other color.
Yeah, perfect. This is one thing, and the other is this thing. This is a two coloring such that there is no monochromatic triangle. So now what we do is by R33, R33 is a number such that it is the smallest number such that any what graph on n vertices when we do like when we color the edges with two colors, there exists a monochromatic triangle of either color. Is the definition of R33. Everyone cool with the definition? What is R33?
Yeah.
Yeah. So our claim is that R33 equal to 6. Can someone simply go through the outline? We just did that. Right.
For 6, we proved that there will exist a monochromatic triangle, and for 5, we had a construction that it does not necessarily have a monochromatic triangle.
You can color it using red and blue and then see how it goes. You can clear it. Okay, so now let me define Kn. Kn is a graph with n vertices with all possible edges. It is called a complete graph. So like K3 is a triangle, K4 is this, K5 is a pentagon, and so on. Yeah, so that is how we define K, and that is like we draw all the possible edges. So now we rephrase the problem. That okay, the original problem that we had was in a group of 20 people. There are at least 4 people who are mutually friends or 4 who are mutually strangers. Now we convert it into mathematical language, that is, consider any graph with 20 vertices. Then there is at least one K4, like if there are 4 mutual friends, then there is a K4 of red color, and if there are 4 mutual strangers, then there is a K4 of blue color. So that is how we define K, what are, yeah, the original problem. Now let us take another example. What is R25? R25 is like the smallest n such that every red or blue coloring of graph on n vertices, that is Kn, it contains either K2 or a K5. Does that make sense?
Yes.
Yes.
Yeah, so that is how we define Rmn, or all m and n. Now, if now the problem is to find different like values of Rmn things, and this problem is what, not so easy as it seems in the case of R33. So, like suppose someone asks us to what, imagine an alien force, and it is very powerful than us, and they're landing on Earth, and they're demanding the value of R55, or they'll destroy the planet. Then it is a famous joke that I mean, he claims that we should master ourselves and mathematicians to solve the value, but no, that is not possible. We should rather what, prepare for alien invasion, because as the numbers grow, the computing the value of Rmn is a fairly difficult job. So yeah, let's look at some possible values of Rmn, which are
2 works, I guess. K2 works.
yeah, yeah. So I'll just like draw some values of Rmn, which are like known. So like this is m and this is n, and here is usual 1, 2, 3, 4, and so on. 1, 2, 3, 4, so on. So yeah, like when m and n, when m is 1, we have like it to be 1, 1, 1, 1, 1 in all the scenarios. Maybe use a different color. When what, m is equal to 2, we have it to be like 2, 3, 4, 5, 6, 7, 8 in this way. For 3, we have 6 here, then 9, then 14, then 18, then 23, and so on. Then here we have 18, then we have 25. Then here is the thing. Here we do not know the exact number, that is, we know the bound that it lies between 36 and 41, but we don't know the exact number. And now, okay, this is the largest known exact number, like the exact largest Ramsey number. Here we have the like, next we have the range 36 to 41, then the range is 49 to 61, and in the next thing we have 43 to 48, and so on. And these numbers grow so large, and the like, if it lies between x and y, then like when the range was between 36 to 41, it could be possible to verify for 36, 37, 38, 39, 40,
But
41.
imagining a graph with 36 connected vertices is really hard.
Yeah, we use computational methods, and yeah,
Yes,
different
yes.
software.
Computation methods needs to.
Yeah. But yeah, like when it goes to R10, 10, it gets really kind of a nightmare. So R10, 10 is known to be between 798 and 23556. It could be anywhere between these two numbers. So I mean, it is computationally not possible to find the exact possible value of that. So yeah, this is how the Ramsey problem begins. That one type of theme is you have to you can try to find the exact value of RMN. Other theme is you try to use probabilistic methods to find the kind of bounds for RMN things. Other thing is you can kind of generalize the problem that instead of uh, 2 coloring, you can have 3 coloring or 4 coloring and see how it behaves. Or you can just restrict to R2M or something of that sort. And there are like many type of problems like that. And you can find asymptotic bounds, you can find hypergraphs, you can look for other monochromatic objects, like you can look for cycles or trees or matchings or mole colors, like you can do whatever you want. So in general, Ramsey theory is how big must a structure be to guarantee that a particular property holds. That is the theme of overall Ramsey theory. That you need to estimate magnitude of a structure so that any particular property holds. That is the idea. And okay, like if I were to put it into some philosophical terms, it could just be like every sufficiently large object includes structured parts. There is some order in large objects and even in very chaotic ones. Yeah, like as you pointed out, like how do we even imagine a graph with like complete graph with 36 vertices? Yes, it seems very chaotic. But okay, there is a famous theorem that our m comma n exists for every m and n. Okay, so then there is this guy. I can't pronounce his name, so I'll just write down his spelling. And yeah, yeah,
Yes, the name is hard.
yeah. So he proposed over 60 pages of Ramsey problems. Like there are like no proofs or nothing. There is just a set of problems, and the name is small Ramsey numbers, and it provides huge data. I can send the link of the thing if you want. There are like many problems that you can try. Yeah, like some kind of doable problems are okay. Here is one doable problem. It is to prove that 43 less than or equal to R55 is not equal to 49 is possible one thing. In 2017, it was proven that we don't need 49 here. We are happy with 48. Yeah, and I mean, part of the proof was very computational. So okay, like the beauty of Ramsey problem is that I mean, it can be tackled in like very multiple different ways. That you can have a computational approach to it. You can use pseudo randomness and probabilistic approach. You can use computer assist Ramsey proofs. You can do pure combinatorics. You can do group theory. You can do permutation groups, orbit stabilizers, like the group theory thing. And yeah, I mean, there are different ways to tackle the problem, and each method has its pros and cons. And yeah, like that. That is the beauty of Ramsey problems. The like interesting doable problem is we can use pseudo random graphs and find asymptotic bounds of these things. Then you can use formal proofs and like you can use different softwares. You can use theorem prover is a software that takes a mathematical statement. Just write it down. So it is a software that takes a mathematical statement as an input and it tries to automatically deduce a proof or let a user interactively build a proof. That is the idea. and the goal is to add certainty to math results. That is again one more method, one more way to do the things. So yeah, like these different approaches are usually used to what find like deal with Ramsey numbers. And yeah, like what we'll be doing today, so that okay, I mean like uh these problems are like fairly tough that we won't be able to what do some proofs or something within an hour or so. So I'll what kind of give an overview that how we use different techniques in mathematics, and if you wish to continue mathematics after your 12th, then what kind of things we'll be dealing with. That is what mainly we'll discuss today. Yeah. So here is a quick exercise for you all. So prove that R34 is less than or equal to 12. I'll wait for a couple of minutes. And once you're done with that, we can what make this bound a bit better. That is part one. You can prove that.
Wait, I guess I have some ID for this R34.
Oh, sorry.
How can I share my ID for R34?
Oh, yeah, sure. Go ahead.
Like for R34, we need like exactly a red graph with
Yeah.
K3 or a blue graph with K4. So for K3, 6 also works. Like you can get a K3 easily in 6. But for
Yeah.
K4, like in 12, we can get like two K3s. And
Right.
these two K3s, I guess, will have to intersect at some common edge. If they do intersect at a common edge, then like either that common edge is blue or either that common edge is red. If that is blue, it can go with any of the vertices. Or if it isn't, then we have
Right. 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 Yeah, right.
okay.
So, kind of to give an outline, here we have 12 vertices. So now we are joining all the edges. So we are definitely joining these like six things. So here we'll definitely get a K3 if that makes sense. And like we basically split the 12 vertices into pairs of 6 and 6, and like look at the intersection, and as he mentioned, the argument is blue, then we can join them, and so is the case with red. Everyone cool with the proof?
Can you please repeat once?
Okay. Would you like to repeat, or shall I?
I would be comfortable if you repeat it.
Okay. So what did you do? So like first you took the 6 thing, right? This is not 6. Yeah. And here you found what? 1 3 complete graph. That is, since we proved that R33 is equal to 6, right? And yeah, like next thing what we do is we just imitate the proof of R33 equal to 6. That like among what? So from this thing, there are 11 lines going, and out of those 11, 6 will be of the same color, and so on. That is the exact procedure that we do. And we then use the fact that R33 is equal to 6.
Yeah, okay, got it.
Okay.
Thanks.
So okay, we got one kind of bound that R34 is less than or equal to 12, but can we make that bound better? Is the question that. Okay. So I'll just what kind of give you a hint to prove that R34 equal to less than or equal to 9. We want to make that bound better. Yeah. So to do so, your first step is you have to prove that R24 is equal to 4. Once you're done with it, prove that every 2 coloring of K9 contains a vertex that does not touch exactly 3 blue edges. I'll maybe type it out.
For any number of the form R2n, we can just prove it is equal to n.
Okay, cool enough. A simple proof.
Like for R2n, we can easily, for n, we can easily get either there is an kn connected graph with the same color,
Yeah.
or either there is at least k2. We can guarantee k2 easily.
Yeah, what is K2? K2 is just a line, right?
Yes.
And it's always there.
And for n minus 1, just note that we can't get kn.
Exactly, right. Because we are in -1 vertices, so we can't have a like graph with an things. So yeah, very important observation. R2 comma n is always equal to n. And from that, it immediately follows that R2 comma 4 is equal to 4. So yeah, that part was really easy. Other thing you can try is that is the font visible? Or
Yes.
yeah, okay, good. Okay. Here is the next step that you can try to prove. And your step 3 is to yeah, let's quickly go through.
What is problem to?
Are you asking for the statement?
Yes,
So
yes.
here we have, yeah. So these are 9 vertices. Then prove that there exists this special vertex such that exactly 6 of them are blue and 3 of them are no, not 6. 5 of them are blue and 3 of them are red. And others. The order could be different, but yeah, the split is 5 plus 3. There exists such vertex is the claim.
Wait, a canine does have such a graph because like if it doesn't have such vertices, then we can, I guess, uh, predict get that R5 is smaller than equal to 9
R55.
or something like that. Some
R55
written
is
number that says
R55 is around 48.
yes.
Could you tell your argument once again?
Let's say there exists no what is such condition. So there is exactly like one color from what is there is exactly like goes like some color goes like greater than equal to 6 or some goes like smaller than greater than equal to 2. Wait, no, wait, no, no, sorry.
Okay, but the issue here is that from this one vertex we have like this 5 and 3 split, but we don't know what is happening in the rest of the area. So that is why we can't conclude that R55 exists in our this thing. That is the issue. Okay, maybe we can this proof maybe at the end of the session, or we can try it for a bit, and I can check your solution or send you my solution later. But okay, the idea is it was like fairly trivial to see that R3. Okay, so what progress we made? First, we R34 is not equal to 12. It was trivial. Now we are putting slightly more efforts to improve that bound to 9 by using simple graph theoretic arguments, and then we'll use some more simple graph theoretic arguments by replacing the less than or equal to sign by equal to sign, and we will deduce that R34 is equal to. That was the general idea of what forming asymptotic bounds, that um, we find some like upper or lower easy bound, we try to improve it, and then we try to get to the equality. So currently the best bounds for RKK, they are between that is the current estimate of RKK for any value of k. And like small factors like changed over a couple of years, but like the main parts of the bound remained the same, like as things were progressing. Then yeah, like you can what uh, prove that r to I equal to I, as we just did. That was easy. Another simple thing that maybe we can try is that I just forgot the notation. That is one thing. One thing you can try. You need like your our typical knowledge of binomial coefficients and identities just to prove that you can what try that thing. Then you can what do the this thing replace a complete graph like we are having km and kn. You can replace it by a cycle or a tree or some special property, and then try to have some bounds. And okay, how much probability do you guys know? Or how much linear algebra you have done?
Like linear dependence and stuff, eigenvalues. So
Okay, maybe that is like not very much to or do the idea of what I was trying to say. How much group theory have you done?
Oh, there was a class on group theory in this camp.
What points did you cover?
It went up till the Lagrange theorem.
Okay, so like, are you comfortable with CM and CN and Curry's products and like that, or maybe not very much?
Oops, like comfortable with what?
Uh, like CM, CN.
Your voice is a bit low.
Audible now?
Yeah, thanks.
Yeah, like, are you comfortable with AM, CN, and those type of groups?
No.
Not really.
Okay, okay, cool, cool, cool. Never mind, never mind. Okay, then let's do something that does not require any formal theory. Okay, maybe I'll just talk a bit about what we do with formal proofs. Do you know the concept of formal proofs? So, like, it is a typical modern trend in math that to use like we use theorem provers to what formalize the mathematical results. Theorem prover is a software that it takes a mathematical statement as an input and like as I explained before, and it either tries to automatically deduce a proof or it allows the what user to interactively build a proof using a defined set of rules reasoning about math. And the goal of this trend is to add certainty to mathematical results. And okay, so like the fundamental idea of these theorem provers is that it contains a very simple and trusted core of all proofs, and they're all built upon each other. And this has delivered many corrected proofs to mathematical results. And yeah, like which is this thing is used. Yeah. So there are some examples of theorem provers. You might not have come across any of them, and that is completely fine. Lean is somewhat popular. You could have come across that. And there are automated theorem provers like E, Vampire, Z3. So yeah, like that is basically what these computer assisted Ramsey theory proofs do. Um, and yeah, like what we do here is that like okay, like first you have to learn these proof what these softwares, and uh, then we use it as a benchmark to compare popular mathy proofs with like the computer aided proofs.
Like most of them aren't like you just type a statement and it works like that. It is like you have to put a certain code which rhythm your taughtiness is in
Mhm.
OMC.
Yeah, yeah. Indeed. So yeah, like um, I guess we wouldn't be able to like cover much of computer aided proofs without what being comfortable with any of these things. Um, but okay, like maybe I was expecting like maybe you would know a little bit of group theory or more of linear algebra thing, but okay, I guess that's fine. Okay. In the remaining time, maybe we can do two things. Like I have two options you can choose. We can get introduced to another class of problems that is usually studied in combinatorics. We call it the rainbow configurations. That is one option. And the other option is we can do some questions from graph theory, like which are like directly or indirectly related to what Ramsey theory. So what would you like to do? Some rainbow configurations or some graph theory proofs?
You can start a poll which people can vote.
Cool.
I guess the host can start poll.
Okay. How do you make a poll? Like I created. It's high.
You need to like edit the poll and then launch it.
Okay, so wait, hold on. Okay, so the question is, what do you want to learn? First one, which is rainbow configs. What was the other choice?
uh, which one did you write as the first choice? You can like we can either do questions like some graph theory questions, which are directly, indirectly, or not related to Ramsey theory, or we can do like there is some very cute set of problems called as rainbow configurations. We can look into that. That would be kind of an overview of like possible UJ research that is typically done. And yeah, like the third option is we can what stop early.
Third
And
option is like stop. Nice.
sorry.
Okay, okay. I think. Can you guys see the poll?
You need to launch it, not create it
Oh,
only.
oh. I'm sorry. Yeah.
Yes, yes, that is just right.
Okay.
Okay. Meanwhile, like we are waiting for the results. I guess I didn't introduce myself. So if some of you did not attend the first session, I'm Rohinee Joshi, and I'm currently a final year student at IIT Bombay. And what I am doing combinatorics and algorithms and complexity theory for living. And yeah, like so I was doing PHP problems when I was an Olympiad student, and I solved that R33 equal to 6 problem. And after that, I was introduced to what Ramsey theory, and I just knew that Ramsey theory is a big deal, and yeah, like there are many people banging their heads, and no one is able to do anything and like that. After my third year, I decided to give it a try by myself. And I was working with a group of people, a group of professors from different universities, and we like it was like big kind of project, and we all were trying to. So I mean, we were like group of people from different domains. Like I do math. There were people who do like lot of CS. They were doing the formal proofs method. There were like people who were doing some group theoretic stuff and so on. And like we all were tackling the like different sub problems uh, by different things. So I spent my last summer doing like trying to prove some Ramsey theory problems, trying to modify some bounds and so on. So like maybe I mean like it is slightly difficult to go too much into depth of one particular problem. The reason being like it is likely to have a couple of prerequisites for some domains of problems. So I mean uh, we would not be able to do that, but I was just thinking that maybe we can give a brief overview of what people do as undergraduate Matthew projects and how the Ramsey theory problems are wanted. So meanwhile, Sunaina, let us know what the poll result.
Yeah, so the results are 75% people are saying rainbow configs, and then 25% people are saying problems related to black theory.
25% are
75% rainbow config, like छह लोग बोल
okay.
रहे हैं like rainbow config के लिए.
Okay, cool. So it is clear thing. Maybe I should have used all 7 colors to get this rainbow config, but no, we don't have that much time. So what is a rainbow config thing? So we are given a group of n people whose relationship to each other can be classified as what? Friends, acquaintances, strangers, and so on. So okay, uh, first thing to notice is that all these problems originated from social science. The Hungarian person who came up with the what study of 20 children and 4 of them were friends and 4 of them were strangers, like that thing that came up from social studies and then it was converted into a mathematical. Similarly, will be doing this here itself. In the initial thing, we were just classifying as what friends and strangers. Now we have different stages of relationships, like friends, enemies, acquaintances, strangers, super enemies, best friends, whatever you call. While we are introducing more
So
human
that's why
relations,
it's rainbow.
exactly. Like either initially we were like coloring the graph with 2 colors. Now we are coloring it with many colors. That is the difference, and that is why we have rainbow configurations. So like the question is, what is the maximum number of trios? Like here, like for now, we are only restricting to 3 people problem that contains one relationship of each type. That is so okay. Let me restate the problem. We have n people. We have different kinds of relationships like friends, acquaintances, enemies, strangers, best friends, whatever you call. And we need to have trio of each type. That is, there should be one triangle of friends. So in mathematical language, there should be one red triangle, one blue triangle, one green triangle, and so on. So okay, the difference between Ramsey problem and this rainbow problem is that Ramsey problem says we either have a monochromatic blue triangle or a green triangle. Here we are saying we should have one blue triangle and a green triangle. So that is one difference. So like that is
But
one
that
thing.
isn't possible. Like in some configuration, you can just like get the whole graph is like a blue
Oh
graph
no, we
collected.
use no. Like okay, we don't have we don't want monochromatic stuff here. So like if we use black and green and red shade, then we don't want black triangle or green triangle or red triangle. What we want is a triangle that has one red thing, one green thing, and one black thing. This is what we're looking for.
So we want all like M choose 3 color configurations.
Yeah, yeah, yeah. Here we are having like three relations here. So like if we have like 7 types of relations, then we should have one 7-sided polygon such that each edge has different color.
Oh,
This is where the rainbow thing comes into picture. So now we can reframe the question as what is the maximum number of rainbow triangles over all possible colorings of the structure.
Rainbow
So
triangles.
this is a rainbow triangle.
Okay.
So okay, I okay. This is a bit difficult to draw the image, the thing, but I'll try my best. We do a random coloring here. I guess I have drawn all the edges. Okay, whatever. This is one possible configuration where we have like 6 vertices and like we have three relations, friends, acquaintances, and enemies. And we need to find number of triangles such that like each edge is of a different color. So like this is one such triangle. This is other such triangle, and so on. So that you can keep calculating the thing. Our question is that we have fixed 6 vertices and we have fixed the three colors red, green, and black, and we go over all possible such configurations, and we have to find a configuration such that the number of these desired configurations. So this is a desired configuration. Number of desired configurations is maximum. That is what we're looking. So yeah, I hope the question is clear. What is the maximum number of rainbow triangles over all
Yes.
possible colorings of the structure? Yeah. Okay, so finding true maxima is like often very difficult. I mean, like imagine very large n.
I guess
But
there will be some sum of some product of sum of binomial coefficients there.
yeah, that is true. But like we can ask some kind of intermediate question that if people's relationships were distributed uniformly and randomly, and they're independent of one another, then can we what achieve the maximum asymptotically? By asymptotically we mean like as n tends to infinity. So, for example, what if things are completely random? Then a trio would have a desired configuration with probability 2 by 9. Like there are basically 3 raised to 3 possibilities for relationships of the trio, right? And exactly 6 of them have like one of each type. So the probability is 6 by 27 is equal to 2 by 9. So this is all possible things, and exactly 6 of them are desirable. So the probability is 2 by 9. So the question is, does the maximum proportion of desired configuration approaches 2 by 9 as n tends to infinity? Or like could people be chosen more carefully to produce more desired types? So let me frame the question mathematically. So yeah, this is our question. Or is the proportion always bigger than 2 by? That is the rainbow problem. And what we can do is we can abstract this problem and ask same question about arbitrary configuration. So like again, instead of like just having triangles, we can do this thing, this thing, this thing, or like any graph theoretic structure we can. So our fundamental question is here, for which configurations would choosing people completely randomly lead to maximum number of rainbow configurations? Let me. And here randomness is assumed, lead to maximum number of rainbow configurations. That is the question. And random gives us best possible. Uh, that is the theme. Now, like we were here looking at graphs. Now we can what look at similar kinds of questions. Like okay, now let us consider this example. That suppose we have this equation x plus y equal to z, and the set 1 to n. Now we are coloring the numbers 1 to n. And so on. And like we will do like 3 coloring of this thing. And we have to satisfy the criteria that x plus y equal to z. Mm, let me come up with a random coloring. Okay. This is the coloring that I have. And my question is a solution. Is a triplet x comma y comma z such that each thing is colored with a different color. So is there any such triplet here right now? Anyone? Any triplet can you find? Any triplet that you can see here in the given coloring? I can see at least one here. So here 3 plus 5 equal to 8 is one such coloring such that each number has different color and they satisfy the thing x plus y equal to z. Can everyone see that? Am I not audible or something?
Oh, you.
You are.
Yeah. So here the conjecture is the above sequence of colorings achieves a maximum. That is, okay. How many such are there any more pairs? Can you see? There is one more thing. 2 plus 6 equal to 8. And these are the only pairs. These are the only 3 rainbow pairs in this configuration. Quickly verify that. Okay, so here is a conjecture. That when we go over all possible solutions, then number of rainbow solutions, number of total solutions. This thing tends to 2 by 5 as n goes to infinity. That is the conjecture. That is one possible rainbow problem. And yeah, like uh, we can what just like graphs, we can replace x plus y equal to z with arbitrary type of question. That a x1 plus b x2 sorry a1 x1 plus a2 x2 up till a k x k equal to 0, the solutions to that. And like instead of kn we can have like sequence of 1 to n numbers. And in both the scenarios we want to determine whether or not some uniformly random coloring of the setting leads to the maximum number of rainbow configurations. So yeah, like okay, here is one open conjecture as of now, that suppose we have 3-term equation, that is ax plus by plus cz equal to 0, where abc are integers. And then when using 3 colors to color like sequence 1 to n, you can always have strictly more rainbow solutions than what you would expect from some completely random coloring. So yeah, like the limit is not really computable. That is the conjecture. So yeah, like these are different kind of questions that people deal with. And yeah, like you would need a little bit of more probability background and some graph theoretic background in order to what answer. For today, like we have covered the proof of R34 exactly equal to 9. We so here here is a hint if you want to try that. And like of course if you like try to prove it and send me a solution, that would be great. Otherwise, if you want my solution, I can send you that. But yeah, I guess this is where we can stop for today, unless you have any questions.
Thanks for the class.